Next, I'd like to welcome you to the Sarp Oral show. It's going to begin with a sort of description and explanation of the OLCF's next generation Lustre file system, and will be promptly followed by the benchmarking panel, which will be led by Sarp as well. Ladies and gentlemen, Sarp Oral from Oak Ridge National Laboratory.
This is, before I start, this is the third or fourth version of this slide deck, and
Did we get the right one?
that's the problem. I'm not so sure after all. So if I got the wrong one, there will be a community fight by the end of this slide deck. I hope that doesn't happen. So this goes forward.
Yes, sir.
Thank you. So this talk will be about our next generation file system, which, thank you. This talk will be about our next generation parallel file system that we will be deploying soon. Soon is the best timetable we have at this moment, so bear with it. The names of the collaborators in this work are listed there, and let's start. So we are moving from Jaguar to Titan. Jaguar was a really nice supercomputer. Titan will be even better than that. So our number of cores will be improved, our memory will be doubled, our peak performance will jump up, our proprietary interconnect will change, which means better I/O rates, higher I/O rates, and you can do the math. So bottom line, we'll have a more capable platform to do science. And that translates into everybody in this room is there will be more demanding I/O coming out of this machine. So we need a new file system to support this as our mission dictates. Yes, that means from Spider, we'll have to go to another file system. We call it next generation file system. We don't have a code name for that yet. I'm sure we'll come up with something catchy soon. So little background on Spider, if you are not familiar with that one. It was the designing, deploying, and maintaining Spider was a trailblazer. When we wanted to, when we started the project back in 2005, if I'm not mistaken, with CFS at the time, there was not a single vendor who can deliver a file system to us turnkey based on our specs. So we had to shepherd first CFS, then Sun, then Oracle, then I think VMcloud, and the storage vendors, and etc., and the network vendors, all the way through this one. So it's a novel architecture. It was one of the largest POSIX parallel file systems in the world when it was delivered. Then it was beaten down by CA, then by K Computers, then by China, if I'm not mistaken. We'll get there again. It's a center-wide shared file system. There are some nice advantages to a center-wide shared file system, and those were the reasons why we went after this architecture. First of all, it eliminates islands of data, which means if your supercomputer is down, you can still access your data through other compute platforms or analysis platforms, whatever. As I said, it decouples the file system from the compute and analysis platform, so you can create a pipeline while you are computing. You can feed it to the analysis cluster and start doing something on that system. It allows you to do rolling or partial upgrades with no downtime since it's decoupled. However, there was a concern that it will be a single point of failure, and when the file system goes down, it will take the whole center down. Turns out that's really not the case. So there's a term called scheduled availability. You can read the definition over the, but basically it says anything that's outside the scheduled downtime for maintenance, and if you notify the users 24 hours, if I'm not mistaken, before the downtime, then it's not considered a downtime. So based on that description, don't snicker, it's not my definition. Which I still think it's a valid description. Based on that description, you see our scheduled availability numbers up there for 2010 and 2011. The left column, 2010 targets and 2011 target, are the numbers dictated by our mission, if I'm not mistaken. And the actual numbers for 2010 and 2011 are the numbers that we achieved. NIP means not in production. So due to metadata performance problems, we had to split up Spider into three. The actual plan was to deploy Spider as a single big file system. Turned out metadata bottlenecks forced our hand, so we had to split it into 50%, 20%, 25%, 25%, three distinct file systems. They are running on distinct hardware. They are three distinct file systems. So those are Widow 1, 50%, Widow 2, 25%, Widow 3, 25%. And the scheduled availability numbers are there. So there's a footnote saying Widow 1 achieved 100% availability of 8 of the 12 months in 2011, which is quite impressive. So that, and combining that as the expected single point of failure, yeah, it's not the case. So it's actually, this is the most reliable component in an unreliable computing environment from our perspective. So this is good. So based on this knowledge, we can safely say our next generation file system will also be a center-wide shared file system. The new architecture, what are we targeting to achieve? We are expecting to have 1 terabyte per second file system level well-formed I/O. That's the official definition. On the random side, we are expecting to get 240 gigabytes per second file system level random I/O. Notice I didn't use the word sequential over there. It's well-formed I/O. And capacity will be based on the selected storage media. It should be between 9 and 20 petabytes. And we are, again, the expected availability will be more than 95%. The availability number is the same with Widow 1 and Widow 2 and Widow 3. So we are at least expecting the same availability level from the next gen file system. So the new architecture in details. It's expected to be built out of SSUs again, like we did in Spiders. There will be a storage backend, there will be some OSSs attached to it, and that will be our building block, so we will multiplicate it as much as needed. That will be the whole file system. The host side connectivity will be IBFDR or QDR, undecided, we'll see. If you are familiar with our Spider network, Spider network consisted of a component called Xeon, Scalable I/O Network, which is the network that connects Spider to Jaguar and all other computing platforms. It's an IBDDR network. So this new network will be a technology refresh and upgrade on that one. I have a diagram I can show. So Xeon does not totally goes away, but it will be upgraded. Disk side connectivity, it's undecided at this point. It can be fiber channel, it can be IB, it can be SAS, we don't know. But whatever it is, as in Spider, it will be agnostic of the host side connectivity. So, another advantage of decoupled parallel file systems, when we are rolling this next gen parallel file system into production, we can keep Spider alive and accessible at the same time. This is a big advantage, so we don't have to move the data when we wanted to turnkey on the next gen parallel file system. So the data can still live on Spider and will be accessible for some time period until its end of life. This is the expected architecture when both Spider and the next gen parallel file systems live concurrently. The left side will be the new components. The right hand side will be the Xeon and old components. It is quite clear. Titan is at top, so if you have any questions, you can ask later, but I think it's straightforward. Yeah, we selected Lustre for the next-gen parallel file system. And this is the slide. I got it correct, so there won't be any fighting, I hope. We will use Lustre 2.2 or later. We have some features that we wanted to see that made up into 2.2. Stuff like improved metadata performance, the detail is over there, and some scalability improvements, also the detail over there. The italic and odd-colored ones are the ones that didn't make the 2.2 yet, but we are expecting in 2.3 or 2.4, and those are the capabilities we would like to have. At this point, I have to be very careful about what I say. At this point, we are working with WAMP Cloud to harden and stabilize Lustre version 2.2 based on our tests as of February on Lustre 2.2 release candidate 1. We will use our scheduled downtimes to harden 2.2 and test future Lustre features, bug fixes, and improvements. We had an I/O workload characterization study in the past. We wanted to see what kind of I/O are we generating on our supercomputer and what kind of I/O are we absorbing on Spider. So this is only an excerpt from that our workload characterization. If you are interested, I seriously suggest that you go read the whole paper because this is just 2 figures that I pulled out of that paper. The left one shows our write-to-read ratio, and the right one shows our small to large message read and write distribution observed directly from the Spider storage controllers. So we use the available tools in the DDN 9900s we have in Spider to observe directly this data. The left figure tells us that although we would love to believe that our file system is a checkpointing file system, that's not the case. We approximately have 60% writes and 40% reads. So reads are, they cannot be unimportant at this point. So we have a heavy mix of reads unexpectedly in our workload. The right one says we have a mixed workload. There are small messages and there are large messages in our workload. Actually, if I can cite the numbers correctly, around 30% or slightly more than 30% of our all I/O is less than 16K. So if you put those two together, our next generation file system cannot be only optimized for checkpointing, and it should also support for mixed workloads. So those two will be the targets we would like to follow. Soon we will start our procurement process. It will be an open procurement. Timetable is 2012, 2013, who knows. We developed some procurement benchmarks based on the I/O workload characterization that I just showed. They are publicly available. I'm sure these slides will be publicly available as well, so you can follow the slides to follow the link to get to the benchmarks. If you are in any way interested in benchmarking, I would love to get your feedback on the benchmarks. We have 2 sets of benchmarks. One is the block I/O, one is the file system level I/O. And yes, on contrary to most of the sites, we are interested in block I/O. So after some study, we decided that the existing block I/O benchmarks are not sufficient enough for our needs. So Dave Dillow wrote an I/O engine based on libaio. The new benchmark is called Fairlio. And in the our procurement benchmarks, we have wrappers around this Fairlio benchmark that generates, that mimics the workloads we have observed in our workload characteristics. So it It generates a list of small and large sequential and random I/O with different queue size and block sizes, and then randomizes this list over all together with different iteration numbers of this test. And then it executes this new randomized list of tests one after another. Therefore, we don't see any caching effects. On the other hand, we are really trashing whatever cache there is in the clients and in the storage system, etc. So it's really designed to kill the storage system and kill the storage system at this point. So that was the target. Our file system I/O tests are structured around the OBD filter survey. We wrote a wrapper around the OBD filter survey, and based on, again, our I/O workload characteristics, it generates different I/O workload scenarios and feeds them back to the OBD filter survey, and then the executed results are got back. And for both tests, block I/O and OBD filter, we wrote plotter scripts as the third component of this benchmark suite. So you just execute the plotter script, it goes through, parses all the results and analyzes them, and then generates you nice GNU plots PDF files and just puts them out there. So it's a whole package over there. And that's it. So if you have any questions.
Oh, sorry, we need to get you a microphone so that you're permanent. Is there a mic?
Yes, over there.
Sorry, Andrew, just want to make sure that you're on tape.
No, I'm guilty. You said 30% or something of your I/O was in what, small 16K or smaller?
Don't quote me on that one. I have to double check the paper to get the exact number, but it's around somewhere like that.
Yeah, I was just wondering, is that the percentage of I/O occurrences, or is that the percentage of data being moved at that size? In other words, is that percentage scaled by, in other words, if you have 90% I/Os at 10 bytes and 1% I/Os at a megabyte, you're still mostly doing 1 megabyte writes. See the difference I made?
Yes, it is the observed number of occurrences for those particular data sizes, block sizes.
Thank you.
You're welcome.
Anyone else?
Good.
Oh.
Do you have your availability numbers without scheduled downtime? Or can you tell us how often and how long your scheduled downtimes are?
Yes, we do.
Okay, I think this concludes the first portion of the Sarp Oral show. I think we're going to move into the second phase now, which is the benchmarking panel.